All right. So today we're going to be looking at chapter 5.5, which is all about properties of logarithms. This one should be a little bit shorter. I'll try to keep it brief. Also, please ignore my homeless appearance at the moment. My heating is down and it is far too cold to not wear something on my head. So let's get started. The first thing we're going to talk about are these two rules called the logarithm of 1 and the logarithm of a. So we're just gonna jump right into the rules. Basically, this video we're gonna have 5 major rules that we go over, and then one little trick, and it's all about just kind of simplifying operations with logarithms. Um, most of them aren't too terribly difficult, so if you feel like you've got a handle on it, you don't need to watch through. I'm gonna save all the examples for the end of this time, so you guys can take off a little quicker. The last few videos have been long, and I don't know how much you guys actually want to see them, but those will be at the end, so you can check them out if you want to. So first of all, there are a couple of special logarithms that are very easy to solve by hand. These first two are the only ones that give you a direct number solution. The other ones will give you like a simplification, but they're the logarithm of 1 and the logarithm of a. Specifically, it's the logarithm base a of 1. That base a can be anything. It can be base 10, so you'd have a normal just log 1, or it can be e, so you'd have natural log of 1, or it can be like log base 2, log base 5, log base 7,000. But anyway, if it's log base whatever of 1, or if it is log base some number of itself. So if it doesn't have a base, remember that's automatically base 10, so log base 10 of 10 satisfies the log base a of a rule. Basically anything, so I could do, log base 2 of 2, or log base 10, which is kind of just normal log of 10. I could do natural log, which is log base e of e. All of these satisfy this log base a of a condition. So log base a of 1 is 0. That's because anything raised to a power, if we're solving anything raised to a power that equals 1, this is always going to be 0. It doesn't matter what the a is. Obviously, that doesn't apply if you have base 0, because that doesn't work, but we don't ever use base 0, so that's not a problem. Log base a of a is equal to 1, and the reason for this is just, anything raised to some power equaling itself, that power is always going to be 1, no matter what the a number is. So, for instance, like I was saying earlier, ln e, remember that natural log is basically just log base e, so this is equal to 1. If you just see log of 10, since that is an assumed base 10, this is also equal to 1. So those are the really easy ones. I'll have a slide a little later that will just summarize all of these, so you don't necessarily need to write them down right now. Next up is product rule. So this is the first of the rules that give you, or that are actually defined as rules. They give you like a formulaic answer, not just a numerical one. There's also the quotient rule and then the power rule. But we'll look at the product rule first. So the product rule states the following. Log base a of m plus log base a of n equals log base a of m times n. In this case, all of these numbers have to be greater than 0, so they all have to be positive, and in general, m and n shouldn't be 1. I guess it doesn't matter if they're 1, but that you could just simplify this to 0 and 0 plus whatever. So not really relevant, but so an example of where this can be helpful is shown here. We have log base or log of 4 times or plus log of 25. So remember, this is an implied base 10 on all of these because we don't have any actual base in here. So we have 4 plus 20, or log base 10 of 4 plus log base 10 of 25. That's equal to log base 10 of 4 times 25, which is 100, and log base 10 of 100 is 2, because 10 to the x equals 100, x equals 2, right? So that's one of the examples. This is obviously a really simple example, but this is where this can be really useful. And the quotient rule, this helps us solve or simplify subtraction of logarithms rather than addition, which the last one did. So the quotient rule states the following: log base a of m minus log base a of n equals the log base a of m divided by n. So using numbers, if we have log base 2 of 56 minus log base 2 of 7, we have that's equal to the log base 2 of 56 divided by 7, which is equal to the log base 2 of 8, which is 3. So two logarithms here that you would not be able to solve by hand. They don't have a numerical answer. You'd have to use the calculator for these. but we can solve this expression by hand by simplifying using this quotient rule right here. And again, I'll give you a chance to write all these down in a little bit. We'll go through some more examples in more detail, but this is just an example of where this one could be useful. So the last rule is the power rule. And this one states that the log base a of m raised to the power of r is equal to r times the log base a of m. So again, if we're looking at a simplified version of where we can use this, here we have the log base 2 of 8 to the 4th. This is equal to 4. We're just bringing this exponent down in front. Equals 4 times the log base 2 of 8. Log base 2 of 8, we discussed earlier, that's just equal to 3. So that gives us 4 times 3, which is equal to 12. Now, this one, technically, if you actually evaluated what 8 to the 4th is, which is 64 squared, which is a huge number, but if you did do that, you could potentially just figure out what the log base 2 of that is. And obviously, if you have a calculator, it doesn't really save you any time being able to type these in. So most of the examples that you'll get in your homework sets are either going to just be simplified by hand, so you're not allowed to use a calculator, or they're going to be things like they're going to include x's in here, and so you're going to come up with an expression at the end. So here's the rule summary. All 5 of the rules are listed right here. I would strongly recommend writing these down. I don't imagine you want to memorize them before your test. Logarithm of 1, that's just the log base a of 1 equals 0. Logarithm a, log base a of a equals 1. Product rule, log base a of m plus log base a of n equals log base a of m times n. I don't know why I used m and n, they sound the same. Quotient rule, log base a of m minus log base a of n equals log base a of m divided by n. This one, it's really important to make sure that whichever number is first, that you're then subtracting something else from, the number that comes first has to be on the top. The number you're subtracting has to be on the bottom. If you do those in reverse order, it will completely mess up your problem. This one, it doesn't matter because it's multiplication, so it doesn't make a difference. And then the last one, log base, or the power rule, log base a of m raised to the power of r equals r times log base a of m. Okay. The last thing that you absolutely need to stick around for and look at is the change of base formula. After I'm done talking about this, I'm going to run through example problems from the book of ways to go through all of these different problems. If you feel like you're comfortable with it, you can move on. You don't need to watch that part, but hopefully it won't take too long, and I think it'll be valuable, so I'd still recommend watching it until the end. But the change of base formula, so basically what this lets us do what it says here is if you want to change the base of a logarithm, there's a way to do calculations with a different base than the problem given. So this is most helpful if you have a calculator that does not let you input bases. So for instance, if I have log base 3 of, I don't know, let's say 412, right? But I have my phone as my calculator, and my phone for some reason only lets me do log or ln, right? This has an automatic base of 10. This one has a base of e. Neither one of those are 3. So I can't really do this problem without converting the problem into a different base. Now, luckily, there is a way for us to do that, and it is as follows. So log base a of x is equal to log base b of x divided by log base b of a. So if I go back to my previous example where I had log base 3 of 412, I can simplify this if I needed to do it on my phone calculator to just log of 412, right? Now we have the implied base 10 divided by log of 3, again, with the implied base 10. We could also do natural log of 412 over natural log of 3. Either one of those you can do. But basically, again, we're doing the exact same thing, right? This top one is the exact same problem, but with whatever base I want it to be. And I mean, I could change it to base 5 or base 2 or whatever else too if I wanted to. There's generally not a good reason to, but you might find one just in a specific problem. And then the bottom one is the same base, so log of the same base, but now we're using whatever the original base was as our actual logarithm. So that gets placed right there. So just really quick, another example of this one. We could do log base, let's say 6 of 54. We can set this equal to, let's say we wanted to convert it to a log base 3 for some reason. We could do log base 3 of 54 over log base 3 of 6. So again, we just changed whatever base we wanted for our numerator, left this the same, but switched the base out. And then for the denominator, we use our same base, but with the old base as our new logarithm. Okay, so that's all the stuff you absolutely need. But we're going to start using some examples or going through some examples. So let's look at this one. This is change of base example. And this one we're saying that I want to solve the logarithm log base 3 of 250, but my phone only lets me use log base 10 or just normal log. So log base 3 of 250 is equal to log, now I choose whatever base I want, so in this case 10, of 250. So we basically left this the exact same, but replaced the 3 with a 10. And then we do log, or divided by log base 10. So again, this is the new logarithm that I want. And then I use the old base as my logarithm here. So log base 10 of 250 divided by log base 10 of 3. Now, you'll notice that you can't use the quotient rule in reverse to split this back up because there's a separate logarithm down here. It's not log base 10 of 250 over 3. It's log base 10 of 250 over log base 10 of 3. So those are different, just in case you were thinking of trying to use it that way. Okay, so then these next ones, these are all example problems using all the different rules. So I will tell you which rule I'm using to solve these, but hopefully you have them written out and can follow along. It might even be worth it for you to pause the video and see if you can do these yourself before I actually walk through them, but that is up to you. So the first one we have is natural log of 3. And remember that the natural log, this one's kind of a trick, is to make sure that you know what this actually is. Natural log is just log base e. So log base e of e, this satisfies our log base a of a rule, or logarithm of a. So this is just equal to 1. So that one's pretty easy. Log base 5 plus log base 4, we're going to use the product rule here. This is equal to log of 20. And remember, there is an implied base 10 here, but all we did is we multiply the 5 and the 4. So now we have log base 20. And this is a little bit simpler to write out. The next one's a little bit more complicated. We have log base 2 of 3e minus log base 2 of e. So this is equal to the log base 2 of 3e over e. And part of the trick of this one is you can see that these cancel. So basically this is equal to the log base 2 of 3. So this is one of those rare instances where this actually makes it a lot easier for you to do calculations with. You don't need to throw extra stuff in here. This one doesn't really change much, to be honest, but that's okay. So this last one, we have log base 5 plus, or log of 5 plus log of 15 minus log of 3. This is equal to, I'm actually going to simplify these ones first. The order here doesn't really matter, and this will make it a little bit simpler to do. So these two, the log base 15 over log, here, I'll just leave the log base 5 the same. And then it's log of, and then we're going to use the quotient rule to start. So that's log of 15 over 3. This is equal to 5, 15 over 3. So basically what we have is log of 5 plus log of 5, which if we use the product rule is just log of 25. And then we're done with that one. So each of these we can simplify it down to either a number or just a single expression, so we don't have to write out multiple terms. Now we're going to go the other way. We're going to expand these functions instead of trying to simplify them. So the first one we have is log of x of y, or log of x times y. So obviously, since we have a product in our logarithm here, we're just going to use product rule in reverse. So this is equal to the log of x plus the log of y. So that one's pretty easy. We're just basically exactly doing the reverse of what we did before, and this one's going to be pretty similar. So this time we have a quotient in our, or a fraction in our logarithm, so we're just going to expand that using the quotient rule. So we have natural log of 5 minus the natural log of z. And then we're done with that one. Now this one's the trickiest. We have to do a couple different things here. So the first thing we want to do is use the quotient rule. We want to get these split up. So this is equal to the log base 4 of the cube root of x minus log base 4 of square root k. Now here we're testing your, or here the book, I guess, is testing your, this should be a 3, testing your knowledge of exponent rules. So you have to remember that the cube root of x is equal to x to the 1/3, and that the square root of k is equal to k to the 1/2. So this is equal to log base 4 of x to the 1/3 power minus log base 4 of k to the 1/2. Oops. And so then from here, we can use our power rule on both of these to bring out these exponents. So we'll have 1/3 log base 4 of x minus 1/2 log base 4 of k. So the reason behind this is when we use that power rule, we're basically taking this power, which would be r in the actual rule if you have it written out, and we're just moving it to the front, so we have our multipliers out here. So this is the expanded form of this one. Okay, and then last example, this one's a little bit more complicated. We're going to try to bring some stuff together here. We've got 5 times log base 3 of x plus log base 3 of 2x minus the log base 3 of y. And we want to write this entire expression as a single term. And we're going to do it without any multipliers either. So first things first, we're going to start by using the power rule here. So the power rule, we have an r effectively times log base 3 of x. So what we can do here is make this log base 3 of x to the 5th. Then we've still got the plus log base 3 of 2x minus log base 3 of y. Now we could do this step by step, but basically since these are in addition, we're going to have to multiply these two terms and then we're going to have to divide it by this term. Right? So in this case, here we'll do log base 3 of x to the 5th times 2x minus log base 3 of y. We could have skipped this step potentially if you wanted to. This is equal to 2x to the 6th. So then we have log base 3 of 2x to the 6th, and then since we're using our quotient rule here, we divide by y, and then we're done with this one. So we used product rule to multiply these two because they were addition. And then we used quotient rule to subtract these two, or I guess to divide these two because they were subtraction. And that's all for this video. This stuff is a little bit, I don't actually know how complicated this stuff is or not. I remember struggling with it quite a bit when I was in high school. This time around, it seems a little bit simpler, but obviously that's more on I don't know how easy it will be for you guys. So what I want to do this week is I really want to try to have more people showing up and asking questions. So if you have problems on homework, especially with this assignment or the next one that you're struggling with, you can even just come and say, hey, Cleary, I was struggling with 13. Can you go over it? And I'd be happy to do that during class this week. But I will see you guys around. Have a good rest of your day.